Okay, so probability, you have met probability several times in previous tests and in different years. So probability, we should remember that probability ranges from 0, means that something is impossible, to 1, saying that it's certain. There are very, very few events that you would say are impossible, and very few events that you would say are certain. Because there's always that niggling, tiny possibility that it could happen. But that's just a whole separate section. They can be represented by fractions, decimals, or percentages. To be honest, the majority of the time we will notice that they will be fractions. And this is the one time that when you give a fraction answer, you do not have to simplify it. If you are not great at simplifying fractions, then do not attempt it. Because if you give an answer as a fraction and then incorrectly simplify it, you'll get it marked wrong. Okay, so if you're not good at it, don't do it, because you don't have to. And you do need to be aware of the relationship between them, and just so that you're understanding what's going on. Obviously, when I say go from 0 to 1, if we were talking about percentages, we would be going from 0 to 100, okay? But if you get an answer in your probability questions of more than 1, it's wrong. So if they've asked you about the probability of something happening and you've got more than 1, you've done something wrong. Probability of an event is the number of favourable outcomes over the total number of possibilities. Hopefully you understand what I mean by that. Oh, so the whole numbers 1 to 10 are written on 10 slips of paper, which are then folded and placed in a hat. One slip is removed at random. Final probability is a 6. So we would say, well, what's the number of favourable outcomes? That means how many of these slips of paper have the number 6 on them? And then how many possible pieces of paper were there? So the probability is 1 over 10. Pretty straightforward, yes? Because there is one slip of paper with the number 6 on it, and there are 10 slips of paper. At least 8. At least 8. 3 over 10. At least 8 would be 3 over 10, because we've got 8, 9, and 10. 12. 0. Oh my God. The board's clearly not fixed. Yeah. So that's 0. Clearly. Complementary events are as they were when we had sets of Venn diagrams. If it was the complement, what did that mean?
Everything that wasn't.
Yeah, in other words, what word did we put in front of it? Not. Yes? So if you've got the complement of something, it's not that happening. So if it was complement of A, it's not everything that wasn't in A. So the probabilities we know add up to 1. Okay, so if you've got the probabilities of all these different events, bless you, we know they always add up to 1. And so that means that we can find the probability of something not happening by subtracting our desired probability from 1, or not desired actually. So the probability it will snow on Christmas Day is 0.15. Find the probability it will not snow on Christmas Day. How would we do that? Come on, lots of you should be able to tell me. Gabrielle.
0.15.
So if it will snow is 0.15, what's the probability it will not snow?
Oh, 1 minus 0.15.
Interesting, you managed to say that without moving your lips.
Oh, I lost the.
So we know that probabilities add up to 1, so you would do 1 subtract 0.15. Pardon? And so 1 subtract 0.15 is 0.15. Okay. Obviously, there can be some slightly more complicated. The ones here, just be careful. I can't imagine you would have any in your exam, but things like sports games, and they'll say the probability of winning is so and so. You must use the probability of not winning to be able to do this method. Because obviously you have 3 options. You have winning, losing, and drawing, or tying, winning. So just be aware it's win, not win. This happening, not happening. Okay. Experimental probability is used if a practical experiment's been carried out. So you could stand on the street and you could count the number of cars, different coloured cars that go past you, and you could record that information. You could toss a drawing pin there millions of times. You could do any kind of practical situation means that the probability of the event is still going to be the same. It's just not it's not theoretical. Okay, so for example, in this situation here, a drawing pin is thrown in the air 20 times. It lands point up 13 times and point down 7. Calculate the experimental probability that a single throw results in the pin landing point up. So, calculate is a strong word here. We don't really have to do anything. It's the probability that it's going to land point up. Well, how many times did it land point up? How many times did it land point up? And how many times did we toss the coin? Toss the drawing pin? Oh, for goodness. So it's 13 over 20. Yep. Because that's the pin. So for part B, it says the pin is then thrown 300 times. Work out an estimate for the number of the times the pin will land point down. Okay? So expected number. So if they've asked you to find how many times something happens, then you'll be using this formula here. You'll take the probability of the event that you're interested in, and you'll multiply it by the number of trials or the number of times that you're doing something. So in our case, we're talking about the probability of the pin, or how many times the pin will land point down. So let's go back to the question, what's the probability of the event landing point down? Oh, God. You know?
7 over 20.
7 over 20, thanks. Obviously my annoyance in my voice is not because of you, but because of this. So that says 7 over 20, very clearly. We would then multiply that by how many times we're doing something. So we're going to multiply that by 300. So we would have 7 over 20 multiplied by 300. Now please note, these are answers that are just number of times. It's not a fraction. Okay, so several times people will write this number over 300. That's not correct. 105. So our answer is 105 times. We would expect this particular drawing pin to land point down 105 times. Do you understand how that works? Yes. So take the probability of the thing you're interested in, multiply it by how many times you're doing it. Now, there are different ways of doing it. You can say, well, it landed 7 times when we threw it 20 times. And if you're doing it 300, you would find out how many more times we've thrown it and multiply it. You get the same answer. Does that make sense? Why it's randomly said? So if this was 20 times, if they said we've thrown it 40 times, you would expect it would be 14. Yes? So it's all in proportion to each other. But this is the best way of thinking about it because the number is not always divisible by your original experiment. Okay? You may have results summarized in the table, so you need to be able to read tables like this and understand what they mean. So the table shows the number of boys and girls in years 7, 8 and 9 at a local school. Find the probability that a randomly chosen member of year 8 is a boy. So here we're just focusing on the year 8 students. So what's our denominator going to be in this situation? Yeah. And what's the probability that that would be a boy? 66. So it will be 66 over 110. Is everyone happy with that? Yeah. B, find the probability that a randomly chosen, oh no, just go away. And that a randomly chosen boy is a member of year 8. Okay, so what's the difference between these two questions? You have more than 2 hands up. Kiara?
The first one was just the year 8 column, and then this one column.
Not quite.
It's the top. No. I don't know.
You were right.
Top column?
Yeah, top row.
Yeah.
Why is it the top row?
Yeah, it's just right.
Yes, so now that here they were talking about year 8s, and here they're talking about boys. And so now our denominator is going to be 208, because we're talking about boys as our focus. And then we say how many of them are year 8, so the same numerator. Yeah?
Yeah. So what five
I did say at the very beginning that this is the one time you don't have to simplify.
Okay.
You can, and often the answers in the textbook will be simplified. You don't have to. Okay. All right. C. Find the probability that a randomly chosen member of the school is a year 8 boy. So here we're going to again have a different denominator. So what's our denominator going to be this time? Gabrielle? 360. Awesome. And this time we want to know that it's a year 8 boy. So what's our numerator? 66 again. Okay, so you can see how the values differ depending on what they're focusing on from a table like this. Yeah? Mutually exclusive outcomes. So these are events that indicate if one thing happens, then the others do not. So rolling a dice, rolling it each, do not affect it. No, mutually exclusive. Right, so rolling a dice, rolling each number would say to be mutually exclusive events, because if you roll a 5, you cannot also roll a 1, 2, 3, 4, or 6. Yes, that makes sense?
It's not possible.
You can't, yeah, so they're exclusive events. So if you rolled a 5 on a dice, then you're not going to be able to roll a 4, 1, and 2 at the same time. If you've got a different dice, then it's a different situation. Yeah. In a pack of playing cards, selecting a heart and selecting an ace would not be mutually exclusive events, because you can select the ace of hearts. Okay, so the events can take place at the same time. All right. If events are mutually exclusive, then to find the probability of one event or another, you would add the two probabilities together. Okay, so you would add probability A to probability B. You have your calculators available to you the whole time, so you don't have to worry too much about things being the same denominator and adding them. So I'll shut up, actually. No.
Oh, right, so there are more outcomes.
Yes. But independent events. Independent events are events where one outcome does not affect any other. They are totally independent of each other. So, for example, tossing a coin and rolling a dice, and getting a head or tail on the coin does not have any impact as to which number you roll on the dice. So they're they're independent events. It may help to summarize. Oh. Yes, I think maybe that makes more sense. Or just summarize the options of independent events in a table. You don't have to, but for me, I think I've said before, I'm a visual person. So Janine has 2 fair spinners. One of them has the numbers 1, 2, 3. The other has numbers 3, 4, 5, 6. Janine spins both spinners and adds the score together. So if I were doing this, I would probably have 1, 2, 3, and then 3, 4, 5, 6. And I know that she's adding the scores together. So I would say, if I rolled a 3 here and a 1 here, my total would be 4. Are you with me? Here, my total would be 5 and 6. This would be 5, 6, 7, 6, 7, 8, 7, 8, 9. So I've been able to summarize my options. This also enables me to see how many options I've got. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 options. Okay? So they're my possible outcomes that I could have. So my denominator here is 12. Work out the probability that Janine's total is 7. What I would do from this table then is I would identify how many of those were 7 and it would be out of 12. Make sense? Obviously, if she was doing something different to the scores, if she was multiplying them or whatever, I would put a different answer in here. Or I may just summarise what my outcomes were. But you can see clearly there are 12 different outcomes. That's if events are independent, then the probability of A and B happening together, you would multiply the two probabilities. So you would find the probability of event A, and you would multiply that by event B. So you would multiply those two. When Laston drives home from work, he has to pass through 2 sets of traffic lights. The probability the first set will be on red is 0.4. The probability the second set will be on red is 0.3. Calculate the probability that both sets will be on red. So, Letty, does the probability of one event affect the other? If one is red, does that mean the other one is definitely going to be red? No, so these are independent events. You happy with that? So that means that if I'm trying to find the probability that both will be red, it means you were finding the probability that we've got red on the first one and red on the second one, which means I'm going to be multiplying these two probabilities together. So you're going to have 0.4 multiplied by 0.3. Be careful when you multiply decimals. This is not 1.2. Okay, 0.12. Because one does not affect the other. So if it's probability of A and B, you multiply the probabilities.
So then,
Yeah. Okay, so it's red and red, 0.12. So you will notice that it tends to be a situation where if you've got probability of one thing and something else, your probability is going to go down. Okay, because you would be really unlucky to get both of them. Okay, so the fact that you see that that's decreased. And calculate the probability that neither set will be on red. So that means you're going to be finding the probability of not red and not red. Well, if I've already found red and red, then I can just do 1 subtract 0.12. Because I know that the probabilities always add up to 1. And so I need to do 1 minus that. Okay, so that will be 0.88. You could have done 0.6 multiplied by 0.7. Oh, that's a different answer.
Don't you count the next?
Neither set will be on red. That's not red and not red. Why is that wrong?
Well, isn't there yellow? Is that what
Yeah, because it doesn't add up 1, 0, 4, 0, 3,
Oh yeah, you're totally right. So you can't do 1 minus because you can have some that don't. Oh, Miss Harrison. Alright, so if it's not red and not red, you're going to do 0.6 multiplied by 0.7. Where do they get those two numbers from? Do you see where I got those two numbers from?
Yeah, from the red and red.
Okay, so if it was red, it means if it's not red, it's 0.6. Okay? And if it was red here, then not red would be 0.7. Yes? Multiply those two together is 0.42, as people were just saying, less than half. Because it could be, one could be red, one could not. So that's why you can't just do what I do, 1 minus. Any questions about that? No? That should all be the stuff that you covered before in probability. Yes? Is any of it familiar? You did, but you probably did that, but you secretly weren't necessarily told that before. Right, so let's also talk about trees. This may be new to you. Have you talked about trees before? So you may be asked to draw a tree diagram to represent possible outcomes and their probabilities. Each branch represents a possible option to the situation. If things are happening repeatedly, i.e. e.g. more than one, be taken from a bag, then the branches will continue to form a tree. So here's our example here. Cat makes 2 chocolate rabbits by pouring melted chocolate into molds and leaving it to set. She then removes the molds. The probability that a chocolate rabbit is cracked is 0.1. Draw a T or even tree diagram to show all the outcomes of 2 chocolate rabbits being cracked or not cracked. So, your branches will always start off with just the number of options that you have. So they told us in this question that we're interested in, is it cracked or is it not cracked? So you're going to have 1 branch that goes towards cracked and 1 not cracked. So far so good? We are taking 2 rabbits, therefore we're going to continue our tree. From this branch we have to have 2 options still, because our second rabbit can be cracked or not cracked. If I followed this option, again I still have 2 different options. So your tree will generally always look 2 here, 2 here, 2 here. If we'd had a third rabbit, we would have 2 options coming from each side. Sure.
No, no,
Right,
no,
coming in?
no, no. I don't know. I don't think
I'm
that's
sure it's
right.
All right, okay, so that's just drawing your tree diagram. Now, it may look super simple to draw them. In fact, when people start doing it, it can go a little bit pear-shaped. So your first one needs to be quite spread out, but not ridiculously spread out. And then your branches will just come off from each of them. To be honest, most of the time they ask you to complete a tree diagram rather than draw it from the off. Okay. So, Gabrielle just asked me, but what about the probability of it? Well, we were told that the probability that a chocolate rabbit is cracked is 0.1. So above the branch of going towards cracked, we're going to write the probability in. So we would write 0.1. We're going to write that for each of my branches that go towards a cracked rabbit. Okay, so all of my branches would be 0.1 in this instance. Now, we need to finish off our tree. So if this branch was 0.1, what must this branch be? 0.9, because we would do 1 to subtract that, yes? And this would be 0.9, and this would be 0.9. So here we've got a summary of our different outcomes. This means that I could have had, so if I were to follow this branch, it means my first one was cracked, and my second one was also cracked. So I have a cracked and a cracked rabbit. Now notice I'm going to actually list them level with my final tree branch. So here this would be cracked, this one would be not cracked. So here I'm going to have a cracked and a not cracked. This one is a not cracked and a cracked. And the bottom one is not cracked. Pretty simple? Yeah? So I just follow my branch and substituted in my probabilities. Now, it's at this point I would probably not do any more work until I've actually read my questions. So I can see that I have 1, 2, 3, 4 different types of outcomes. Okay, that doesn't mean that our denominator is going to be 4 though, because our probabilities of these events happening are not equal. So it says calculate the probability that both chocolate rabbits will be cracked. So of my branch, on my tree diagram, which path have I followed if both of them are cracked? So which path have I followed? Have I gone here and here? Have I gone here and here? Shayla, which path have I followed? The very top, yes? So I've cracked and cracked, yes? Now, listen to the words I'm saying. Cracked and cracked. What did I say about when we hear the word and? What do we do with our probabilities? You multiply them, yes? So if you've got a cracked and a cracked rabbit, you will be calculating 0.1 multiplied by 0.1. So cracked and cracked indicates multiplication. So we would have 0.01. Next question. Work out the probability that one of the chocolate rabbits. Yeah, that's it. Why don't you like it? I thought this is a nice one. It's pretty straightforward. Because the probabilities are different. Okay? So if the probabilities were all the same, you wouldn't need to write any probabilities in the tree itself. But because the probabilities are not, so you have to follow these. So the next one says find out that one of them is cracked. So how many situations here am I looking at where only one of them is cracked? Two different ones, yes? I'm following this path and also this path. So to find the probability of this event, it would be cracked and not cracked, so I would multiply those. So it would be 0.1 multiplied by 0.9. To find the other probability, I'm going to again multiply them. So that's going to be 0.9 multiplied by 0.1. Now what do you think we're going to do with these two numbers? You're going to add them, okay? So what's happened is that we've got this situation or this situation. If we ever hear the word or, we will add our probabilities together. So this situation or this situation, we're going to add them. So you're going to have 0.09 plus 0.09 gives us 0.1. Now, to make sure that you've done things right, as I said, once you've drawn your tree, you can leave it like that. If you seem to have quite a lot of time on your hands, you could multiply everything and put it in your tree to start with. So you can write this as 0.01, 0.09, 0.09, and 0.81. Okay? If you do that, then what should you find about these numbers here? They should add up to 1. So these values here that we have should always add to 1. If they don't, you've made a mistake. So if you've got time on your hands, that's a good way to check stuff. If you're wrong, then you go back and just double check perhaps your multiplication is wrong. Okay. And again, if you do these questions and you get 1 point something, you've made a mistake. Probably in your head multiplied incorrectly. Alright, another example. 2 torches, 1 red, 1 black, with few batteries. The probability that battery lasts for more than 20 hours is 0.7. Draw a tree diagram to show the probabilities of torch batteries lasting more or less than 20 hours. So they've helped us out by telling us what we're interested in. So, first is a branch, more than 20, less than or equal to 20. Okay, so that's torch 1. You can label it red torch if you wish, doesn't really matter, but we're talking about 2 torches. I'm going to have the same options when it comes to my black torch. Okay, so that's my black torch. And then my outcomes are on the end. So I've got more than 20 and more than 20. More than 20, less than or equal to 20.
Are the outcomes necessary for these?
Most of the time the diagram will expect you to write them in, yes. But it should have some kind of indication that they want that. So we have 4 different options, but they're not all equal probability because they told us more information. They said that the probability that it lasts for more than 20 hours is 0.7. So on each of the branches that it has more than 20 hours, we're going to type 0.7. And 3, what am I going to write on the other branches?
0.3.
Why?
Because when there's different values.
Yeah. Now, so far all our questions have been decimals. They may be fractions. And so it could be a situation that you need to be dealing with multiplying and adding and subtracting fractions. But you have your calculators to help you. Okay, so far so good?
Wait, what did you write for the black in the middle?
Just that this is indicating my red torch. This was my black torch. I've had 2 separate situations going on. You don't need to label them red and black.
Okay.
It's just that you to recognise there are 2 different torches.
Okay.
Find the probability that the battery lasts more than 20 hours. In both torches. Okay, so in both torches we're going to have this top branch, yes? So that's going to be 0.7 multiplied by 0.7. Which is 0.9. And it's in situations like that, the 0.7 multiplied by 0.7, I've seen so many people write 4.9. So just don't do that. In only one torch, again, you're looking at your 2 middle situations. So you've got 0.7 multiplied by 0.3, 0.3 multiplied by 0.7, and then you're going to add them. Add it? When to do what, sorry? So whenever you've got a situation where you're talking about things happening, so we want to know about the 2 different torches, you would multiply. But because we have in our outcomes, we've got both this one and this one, where one of the torches lasts for more than 20 hours. So you find the probabilities of each of these individually by multiplying. So that was the 0.7 multiplied by 0.3, 0.3 multiplied by 0.7. And because we had 2 separate ones, we would then add those 2 together, because we're interested in both of those. It's just that you have to see the board. So, the last one in at least one torch. So at least one torch, we've got options here. At least one torch, we've got this one, or this one. Agreed? Now, our question, we've worked out the top one, and we've worked out the middle 2. So what we could do is identify that that's 0.49 plus 0.42. Because this was both, and this was at. No, this was 1. So we were able to add those 2 together, and so we get 0.91. Right? However, you're not always going to be asked these questions initially. So what we can also say is, well, this is the only situation that we don't want. You see that? So this is the only situation we don't want, and we know they all add up to 1. Well, then maybe it's quicker to find this one and subtract it from 1. So we alternatively we could have done 1 subtract 0.9 multiplied by 0.9. No, that's not the question. What are the numbers? 0.6.
Well, why would you
0.3. because, as I said, if this was the only question you were asked, you would have to work out this one, and this one, and add those three numbers together. It just so happens in this question, they had already asked us about those, so I was able to quickly add them. Okay? But if that was the only question they'd asked you, then it would be faster to do this. So that's going to be 1 subtract 0.09, gives us, funnily enough, the same answer.